The next speaker is Dr. Christopher Curtis from San Diego State University. And the title of the lecture is Nonlinear Waves over Deepwater Shear Currents and Stokes Drift. Dr. Curtis, could you start, please?
Of course. Thank you so much. I mean, tough act to follow. That was a wonderful talk we just saw. And really, I'm extremely grateful because it set up so many wonderful ideas that I'm going to be speaking about as well. So no, it was really, really well timed. So you've had a chance to look at the title. This is joint work in particular with Henrik Kalisch from the University of Bergen and then John Carter from Seattle University. But there's a little bit in here I snuck in that's work I did with a former undergraduate student of mine, Mackenzie Murphy, who I think went on to work with the Navy. So, you know, once you start in water, you just kind of stay there. So anyway, as for motivation, Stokes drift, you know, just absolutely one of these centrally important concepts in fluid mechanics and oceanography. Right, and really comes down to the idea that as you have, right, water waves moving by, right, particles don't necessarily get advected by the wave itself per se, but especially because of nonlinear, right, transport of the energy in the waves, right, you get this separation of orbits, right, points don't come back to themselves, and this is what actually allows for there to be, right, transport due to wave motion. And I'm not really a proper oceanographer, so I'm mostly saying things when I talk about something like, say, Langmuir mixing that I know the big kids on the playground, such as its Scripps, talk about. But absolutely, one of the big reasons to understand Stokes drift is it becomes a central part of the theory of Langmuir mixing. See, for example, Craig Leibovich's paper from JFM in 1976. And the idea of Langmuir mixing, right, is due to forcing from the wind, right, you have these rotating cells that set up underneath the water, somewhat like Bernard convection. And this ultimately leads to the formation of wind rows along the surface of the water. And now, while this is a relatively, like, you know, toy example, Langmuir mixing is a central mechanism for transport in the open ocean from upper surface regions down to, you know, couple hundred meters of depth below. So this becomes a central part of like nutrient transport, among other things, in oceanographic contexts. More classically, we can go back, of course, to the seminal paper of Longway-Higgins from 1953, which is one of the first papers to really look at Stokes drift in really deep quantitative detail. So this is something that's been around for a while. Now, despite its long and storied history, it turns out that some later experimental results, there's a paper by Smith in Journal of Physical Oceanography from 2006 that looks at data collected off of the back of a boat with a radar array. And then there's a paper by Monosmith in 2007, which is wave tank experiments. And both end up showing in a number of different scenarios that the classical theory of Longway-Higgins and what it would predict in their sort of live oceanographic contexts and controlled experimental ones, in neither case does it really apply. And one of the big things that confounds the theory in these papers is that Stokes drift seems to vanish. It should be there, but when these individuals go looking for it, they don't find it. My collaborators and I found this to be really kind of compelling. And then we can't directly speak to either the oceanographic context in Smith or the experimental context in Monosmith. We're going to ultimately turn this into a math problem we can get our hands on. But ultimately, we find a math problem we can get our hands on that at least shows, right, once you start including other effects, other fluid mechanical effects, that's when you're able to start getting things like Stokes drift to disappear. We'll talk about that in a bit. I mean, arguably, it's kind of the longer point of the talk. So what we also sort of picked over or got motivated by was the fact that a lot has been done when we talk about Stokes drift to understand it at the linear level, especially under the impact of shear currents. And there's some seminal work by Craik in the 80s, and then by Phillips later in the early aughts. So in that case, they look at pretty general shear profiles, very much in the vein of like what you would study, in classic fluids, leading to things like Kelvin-Helmholtz instabilities and what have you. But they don't really take their asymptotics far enough to start looking at nonlinear effects. And to be fair, were they to try and do that in the setups they have, that would be a daunting task, to put it mildly. So we instead are going to come at this from the point of view of really trying to understand, how does nonlinearity in the surface waves play a role in all of this? And to do that, that means we have to be a little more restrictive in how we deal with shear currents, and we have to look at a much more specialized kind of shear profile. And so that means, for us at least, constant vorticity profiles. So they are technically shear profiles, but they're strictly linear, and in some sense kind of represent the simplest non-trivial amount of vorticity you could introduce into the problem without having to get into something far more technical. So with that simplification in place, we are able then to sort of repeat the derivations one would use, right, to derive nonlinear Schrodinger equations for free surfaces, so that we can look at nonlinearly modulated wave packets, right, interacting with right, constant vorticity shear profiles underneath the waves. And that lets us do a few different things. But to really get at Stokes drift, it became clear that the best way to do that, the most mathematically consistent way to do that, is to introduce the generalized Lagrangian mean machinery, as we saw in Nicholas's talk just a second ago. Although that does require some insights for us, especially because I think the way that a lot of people have treated free surfaces within the GLM framework is not always terribly clear. So we really had to spend some time hammering that out. But ultimately, as we will show, constant vorticity interacting with nonlinearly modulated wave packets does actually create conditions in which you can completely quench Stokes drift. And so while that doesn't necessarily address the lurking, if you will, dilemmas, right, brought up by these papers, insofar as we can't recreate either their oceanographic or experimental environments, at the same time, it at least points to an idea that with a bit more work and modeling, there's a way to probably wrap our heads around these results. And we feel that our work is kind of a first tentative step in that direction. So just to give you an idea how we set everything up. So our fluid velocity U is such that, in some sense, to leading order, we have our constant vorticity shear profile. Again, Z is the vertical dimension. And this is just in 2 dimensions. So we just have a surface going along the horizontal and then bulk moving in Z. So here's our constant vorticity shear profile, and then an otherwise inviscid irrotational potential giving us the rest of the fluid velocity. And then a natural boundary condition that the vertical velocity vanishes as we go to infinite depth. Asymptotically, we treat our vorticity as an order 1 term. And once you do the normal rescalings that one does when doing nonlinear Schrodinger theory, we get an epsilon order free surface displacement where our surface displacement eta in the horizontal and time dimensions gets expanded, right, in the following harmonic wave form or Fourier series style form. Probably the one thing to keep in mind here is that the order 1 vorticity elevates, if you want a consistent asymptotic approximation, the order 1 vorticity actually elevates the mean fluctuation of the surface. Traditionally, in strictly irrotational context, this should come in as an epsilon squared term. And that's not what happens here. So there's a mean current effectively of the surface that gets bumped up because of the presence of the vorticity, which in some sense kind of makes sense. But it's probably one of the most immediately recognizable physical effects that comes out from the introduction, right, of some degree of rotation in the problem. And then our harmonics theta are characterized by some particular wave number k naught, an affiliated dispersion relationship. The first slow variable travels with the group velocity of the packet. And then of course, everything gets modulated on a yet slower time scale, which is completely typical of, NLS style expansions. So unfortunately, it became very clear, in particular because of this elevation of beta naught, that if we really wanted to get into this problem, we were going to have to go beyond just the order of NLS and actually go an order higher to what would normally be called, say, Dijkstra equations. And this does make things technically more complicated. Likewise, vorticity dependent NLS models have already been derived. There's a paper by Thomas and Carif from Physics of Fluids 2012 where they work all of this out. And so coming along later, we also realized we just needed to go further so we could, add something more to the community. But going higher order to the Dijkstra equations isn't just that. It turns out we actually really do need that order of approximation for everything we do later, especially if we want to have any impact of nonlinearity in our Stokes drift computations. So I will spare you watching an unholy amount of math go by to get to vorticity dependent Dijkstra equations. One way you can write them is in this coupled eta naught, again being our mean term for the surface, and then eta 1 in some sense being the dominant nonlinear response of the surface. And it's highly non-trivial, as you can see. Likewise, also keep in mind this script H is a Hilbert transform, so these are also non-local problems. So a number of effects really kick up, tracking the interaction of, in some sense, the fundamental fluctuation of the free surface from its mean response. Thankfully, using this particular equation here in terms of eta naught, without too much fuss, you can solve for it in terms of eta 1, and then ultimately close this system, do a little bit more math, and get something that looks a lot more immediately recognizable as a perturbed nonlinear Schrodinger equation. Because clearly here, to leading order, we have, right, the classic NLS model. Let me just point out real quick that the coefficients alpha D, alpha sub n sub L, and then everything else can be looked up in our JFM paper from 2019. They're pig's breakfasts of expressions that should not be written down explicitly on slides if you can help it. But it can all be hashed out, and it is written down. So anyway, so despite all of the gore, ultimately you can actually get something that's really actually pretty manageable. And of course, it's pretty manageable from the point of view of doing numerics, which is really what matters the most for us in the long run. And just to fix a bit of terminology, if these coefficients alpha sub D and alpha sub n sub L have the same sign, then we're in the focusing nonlinear Schrodinger or nonlinear Dijkstra case. And if they have opposite sign, then we're defocusing. And again, as one would expect from going to higher order, we get higher order dispersion and then a far richer array of nonlinear effects. And again, also non-locality by way of this Hilbert transform. So one thing we felt compelled to speak to is we actually kept surface tension in our model. And in the work from Thomas et al. In 2012, they were able to show that modulational instability in the focusing case could be suppressed. And we largely are able to show something similar, except surface tension doesn't make this true for all wave numbers. Now, the black represents modulational instability suppression. The white means it's active. So you can see here, there are these regions where there's really only a very limited number of wave numbers that are in some sense active from an instability point of view. But surface tension, unfortunately, does keep it such that modulational instability can't be completely suppressed, even with vorticity in play. And this will matter in a little bit when we talk about different examples where we want to look at Stokes drift being quenched. In particular, it means that anytime we see Stokes drift being quenched, for us, we're always going to be looking at that in the defocusing case, because the focusing case, from the point of view of water waves, is still nominally unstable. Now, on that note, kind of going to the bigger brother of classic, modulational instability, which is really just looking at perturbations around one plane wave. With Mackenzie in a 2020 paper, we were like, well, hey, we spent all this time deriving the DISA equation with vorticity and surface tension. And so what that allows us to do is think about doing statistical studies where we look at random wave fields. And so our random wave fields in this case are essentially going to be random phases, and otherwise everything pulled from just Gaussian distributions. Sorry, that was a misspeak. The only randomness is in the phases here. It just looks Gaussian, but there's nothing random about this at all. It's just a particular choice. And it's nice to have it this way for a number of reasons. Anyway, I mean, I guess it's a Gaussian distribution in the wave number when you look at the initial condition, and then you see how it evolves from there. So there's somewhat now classical results that say when we look at, in the focusing case, so that we have same sign here, the affiliated Benjamin Fear index, which is a balance between those coefficients of nonlinear dispersion and then roughly the amplitude of a random wave field divided by its width. If BFI is under 1, which is to say our width is sufficiently wide, then we anticipate that our wave field is statistically stable, which is to say it starts Gaussian and then it should roughly stay that way for all later times. And there's a paper by DISA and company in 2003, which looks at this in the context of no vorticity. And so we said, okay, well, let's see what happens when we add vorticity. And what we're able to show is that, I mean, roughly speaking, that BFI condition is correct. So if we look at the kurtosis, which is to say, in some sense, the degree to which we really deviated from Gaussianity in our initial distribution, as we see for both the NLS and DISTA model, that's always going to increase as our BFI gets closer to that 1 threshold, which is to say we're getting further and further and further away from Gaussianity, which is what we start from, which in some sense is going to be our instability measurement. But we also see that DISTA, which always ends up on the top here, right, really is always adding more kurtosis, is giving us, right, more deviation away than what NLS alone would predict. And right, while we can't necessarily derive analytic formula for how all of this then changes in terms of different shear profiles, so in this case, this one is counterpropagating against the surface flow. This one is going with it. And we see once we're going with, right, we get dramatic enhancement of the kurtosis response, especially at the level of the DICE equation. So if nothing else, this also shows us the value of deriving these, right, closed form asymptotic models for water waves. They may not necessarily be as immediately relevant to, you know, hyper detailed oceanographic modeling, but they really do allow us to address some statistical questions that would be extremely difficult to do if when we're trying to do more like full scale simulations, say like using particle methods for ocean dynamics. Now, on to the GLM machine, which was really a journey for me, to put it mildly. So again, our fluid velocity split up over coordinates now is going to come down to the impact of our constant vorticity shear profile, and then an order epsilon harmonic function contribution in the horizontal. In the vertical, it's just all down to that harmonic function. And so to get at the Stokes drift, again, we're going to use this generalized Lagrangian mean approach. And if you're not familiar with that, I certainly really wasn't when I started. The idea here is that we start from some chosen Eulerian averaging operator, which in this case, following Whittam, is just going to be averaging with respect to those fast phases theta that we used in our NLS expansions at the beginning of the talk. But then to actually understand how averages, right, work as we travel with particles along the flow, i.e. in the Lagrangian frame, the way that we're going to get at that following the work of McIntyre and Andrews from the 70s is by way of using these near identity transformations of the form x plus epsilon y xt. So the idea with generalized Lagrangian mean approaches is that you're kind of always starting on one set of coordinates or on one manifold and actually mapping things over into an equivalent one and then trying to track what happens to your physics as you do these mappings, with the added requirement that your Eulerian operator, right, treat your near identity perturbation as a zero average term. And in some sense, this becomes ultimately a kind of closure condition that gets all of this to hang together. So to get at the Stokes drift, once we have an idea of how to find the affiliated average Lagrangian velocity, and of course we can just directly apply our Eulerian average to our fluid velocity, the Stokes drift is the difference between these two things. So in some sense, one thing to keep in mind is I can always, if you will, naively compute this. I have to be clever to compute this, but then once I know this, I can get at Stokes drift. And so what worked for me ultimately in understanding how to really compute the affiliated Lagrangian average of the fluid velocity is that through hook and crook, you can reduce it to a question of finding its affiliated curl and divergence. Where the curl of the Lagrangian average of the fluid velocity comes out to be the curl of the affiliated pseudomomentum, and then we have our constant vorticity times the Eulerian average of the Jacobian of the near identity transformation. And then likewise, the divergence of our average Lagrangian fluid velocity effectively has an affiliated mass conservation equation that it satisfies. But once you have everything written this way, despite any complexity that sort of appears at first, after a minute you realize this is just perturbation theory and PDEs, and you just go from there. Really, the only last thing you have to lose sleep over are boundary conditions. And that was the real trick, was understanding how to port your near identity transformations in the bulk, but also at the surface, and that you needed to be a little bit careful about how you did that in order to get a completely consistent asymptotic scheme. There's actually a paper from a group of oceanographers in France from the mid-aughts that does this. They just do it in their literature so fast that I think I didn't even know about it until in review. And then I was like, oh, look, they did it too. So anyway, moral of the story, once you really nail down the boundary conditions in the GLM framework, it all just kind of turns into a surprisingly straightforward problem in perturbation theory. The one thing I'll say is that when you look at, because again, keep in mind, we're doing everything over infinite depth. And it does turn out in your perturbation theory that, well, I mean, again, ultimately, we're most interested in surface dynamics and specifically Stokes drift at the surface. You can show that you're going to get some kind of singularity formation, at least relative to the order of perturbation theory you've done in the bulk, which would usually indicate the formation of cat's eye like patterns. This is something that we didn't need to immediately address in our work, but it is definitely a fascinating question for future research, and is very much in the vein of, say, like the numerical results you see from the papers by, say, like Peregrine and De Silva from the late 80s, which is some of the first really sophisticated studies of free surface waves over constant vorticity shear profiles. Anywhatsits, with all of the hideous math out of the way, we can ultimately show what the surface Lagrangian average of the horizontal velocity is, and ultimately then figure out which vorticity values for a given wave number of our wave packet at the surface we need to pick in order to zero out the Stokes drift. Of course, this is all wonderful. What we really want to see are some plots, though. So to generate plots, which everything is done numerically, when we look at the focusing case, we're going to use exact solutions to the NLS equation as initial conditions. And so our preferred choice there are going to be those generated by Jacobian elliptic functions of the following form. So these are senoidal solutions, right, which vary in terms of this elliptic modulus kappa. Now, all of this gets done ultimately in the Vord-Dijkstra equation. So really this just gives us initial conditions at tau equals 0 for the Vord-Dijkstra equation, and then we evolve forward. And then as we evolve that surface evolution forward, right, we then also track fluid velocity at the surface so we can trace particle motion as waves go by. All of our numerics for the PDEs are done with pseudospectral schemes. All of the numerics to track the evolution of the affiliated differential equations for the fluid velocity at the surface are done with just standard fourth order Runge-Kutta schemes. So that's the focusing case where, right, again, my coefficients in the NLS model for dispersion and nonlinearity have the same sign. Similarly, with defocusing, we can then look at either plane wave solutions because we don't have modulational instability, so they're actually more physically realistic things to examine, or we can look at the affiliated Jacobian elliptic solutions, which in this case are sinoidal, not senoidal, but sinoidal, but effectively kissing cousins, right, to the focusing case. Okay. So in the defocusing case, again, looking at these S-noidal solutions, so the parameter really to keep in mind here is the varying elliptic, right, modulus. The smaller the elliptic modulus gets, or the closer to 0 it gets, the more we're basically just looking at linear, i.e. plane waves, or simple trigonometric solutions. The closer kappa gets to 1, the closer we're starting to look at effectively dark solitons. So if you will, much more proper nonlinear waves. So the plot on the left here is kappa is a half. So this is more to the linear regime. Over here on the right, we have kappa is 0.99. That's getting closer to 1, which is again getting us closer to kind of the classic dark or defocusing soliton case. In either way, using our Stokes drift results, we're able to pick constant vorticities, right, that show us ultimately that our fluid particles end up on closed paths. They kind of spiral out and then fall onto limit cycles and in effect get stuck. So in that sense, yeah, at this point we've quenched Stokes drift and cannot have mass transport. And again, this doesn't address those compelling and intriguing experimental and oceanographic results, but at least hints at an idea that a balance of added physical effects from vorticity and nonlinearity can interact in such a way to make Stokes drift disappear. Similarly, if we look at the defocusing case with plane wave solutions going by, we can also figure out what the right vorticity profile should be to get nearly closed orbits. Just for completeness, we can look at the focusing case where you can see now that things actually move along as the waves go by, which is nice. These are relatively nonlinear wave profiles going by. Again, kappa is close to 1. So those sphenoidal solutions are relatively close to the bright soliton, since this is the focusing case. And likewise, we can see, so here we have no vorticity. Here we have vorticity going, I apologize, against. And this is, no, this should be the counter-propagating. This should be co-propagating. So this tends to enhance motion. This in some sense kind of gets things to stand relatively still or not move very far relative to their initial position. Another thing that comes up, and this echoes in part the cat's eye patterns that I was talking about earlier, we see in our asymptotics that there are vorticity profiles which would cause massive spikes in the affiliated horizontal velocities at the surface, or average velocities at the surface. And clearly that means our overall NLS/DISTA asymptotic approximations are not pertinent there, which is to say that our theory has broken down around these particular vorticity choices. And so it's some kind of higher nonlinear resonance that needs to be accounted for, but our order of asymptotics doesn't capture it. And again, that's another subject, definitely asking for future work. And where am I in time? Okay, so this is about right, groovy. So in conclusion, we ultimately in our work derived by way of the DISTA model, a higher order modulation equation accounting for constant vorticity shear profiles over infinite depth. And we've shown across a variety of different cases, that this allows for strong impacts on mean flow properties to occur, and in particular, that we can get mean transport things like the Stokes drift to all but disappear. But in some cases, we can also, as we saw with our focusing waves, enhance transport, which would make sense, there's ways in which we would think if you're moving in the right way relative to an underlying shear profile, this is going to get things to go further than you would expect otherwise with no vorticity in place. And then, as I've alluded to at a number of different points here, higher order asymptotic theories would have to be derived to account for both some interesting singularity phenomena that pops up in the bulk when we do the generalized Lagrangian mean computations, and then likewise what happens in mean surface velocities or Stokes drift velocities at the surface. Although to be fair, I do have deep sympathies for anyone that comes along to try to do that. It will not be trivial. The computations are involved, to say the least. But I mean, also quite intriguing that they be done, because clearly they're pointing to more physics that I think the community would do well to learn about. So with that said, thank you for your time. Appreciate it.
Thank you very much. Thank you very much, Dr. Curtis, for very interesting presentation. Thank you very much. So let's open questions and comments. Any questions? Yes, Nick, please.
I just start with a comment. I think that's a heroic level of computation you did, particularly diving into the generalized Lagrangian mean theory.
Yeah.
I've poked around this problem, and I'm just saying this as a comment just to facilitate discussion, but I work directly in the Lagrangian frame, and what's nice there is you have Gerstner's wave to expand about. So
Sure.
You can think of Stokes waves as being corrections to Gerstner waves, you know, asymptotically, and some of that kind of falls out. I was wondering, you know, have you thought about working directly in the Lagrangian frame and don't mix and match?
I think so. That's a really, really good question. And that haunted me. Right? Because why does it haunt me? It haunts me because when you go read, in particular, Professor Salmon's paper on generalized Lagrangian mean averaging, he's like, you can choose not to work in the Lagrangian or the Hamiltonian, but you're making your life much, much worse. And he recommends that you not do that. And he's right if you can help it. The problem though is where are you going to get the Hamiltonian? So I have a Hamiltonian for the full water wave problem. But if I work at that level, then NLS relative to that becomes a much higher order theory on much longer time scales that lurks off in the distance relative to, right, the variables you would naturally want to work with in that framework. Now that's okay, because you can say, okay, but then we bump down to NLS, and NLS has its own Hamiltonian, so do everything there. But the problem is, at least as I saw it at the time, now I will fully admit, I am trying to remember how I was thinking about 4 years ago now. And it's a little dusty. But the Dijkstra equation does not have a ready Hamiltonian formulation. So doing modulation theory in that sense there, that way, and again, we really did need the Dijkstra equation, or at least that order of asymptotics, to get our results to hang together correctly, and to be, you know, asymptotically consistent. And so I think that's what ultimately motivated me to just, in some sense, come at this directly, because if you sort of use the naive GLM approach, once you nail the boundary conditions down, right, it's just that div curl problem, and then you just expand. Now, what's ironic here is that one of my collaborators, Henrik Kalisch, has a series of beautiful papers looking at how to, from the full water wave problem, derive affiliated Hamiltonian asymptotic approximations at whatever order you like. And so frankly, we should have probably started with his very good result there, and then pursued the Hamiltonian GLM perturbation theory in a more internally consistent way there. And I think it didn't occur to us at the time to try that.
No, it's a lovely piece of work. Thanks.
Yeah, for sure. Thank you.
Thank you very much. Any other questions? Okay, may I ask you a question? Yes, please. Dr. Maru, please. Yes.
Chris, thank you very much for your great talk. Is the defocusing case happen in the water wave? You mentioned about defocusing.
Yeah. So at least as I tend to think of it, I think of the defocusing case as being more typical for waterways, but that's a good question. I need to go back and double check that. Because I understand what you're asking. There's one that's more typical, one less. And I can't remember, part of the problem sometimes is what people mean by focusing versus defocusing, right? Can vary slightly depending on context. So that's why I was also very careful at the beginning to say what I mean by focusing is same sign versus opposite sign. And I feel like the dark soliton case is the more typical one in ocean waves. We wouldn't necessarily expect deep water bright as much. That said, the person who would know off the top of their head is Ben Akers, and I'm suddenly desperately worried that he would say I'm dead wrong. So I'm going to hedge a little at this point.
So you showed elliptic functions solution. That exact solution. Exact
well,
solution.
so it's an exact solution to NLS. We use it as initial conditions to the Dijkstra.
NLS. So not exact solution for your equation.
No.
I see.
We just took them as sort of the most like typical family of profiles over periodic boundary conditions for deep water nonlinear water wave evolution.
I see.
And especially because we have that elliptic modulus to play with, that lets us kind of look at a variety of different phenomena under one common sort of like phenomenological umbrella.
Okay. Thank you very much. Thank you.
You're welcome.
Okay, thank you. Any other questions? Okay, may I ask a question?
Sure.
I'd like to make clear the difference between your model equation and the another nonlinear Schrödinger equation derived by Thomas and Khalif. And both of them are nonlinear Schrödinger type approach, I think. But in your model, omega is assumed to be order 1.
Yeah.
And in their model, Thomas model, omega is assumed to be order 1.
It would have. So if I remember how the math all hashes out, it would essentially have to be, whether or not they stated that explicitly. If they made it smaller, it would necessarily push that mean term down a lower order, and you wouldn't necessarily see the impact of omega show up at the NLS level. Another way I can answer this is, to the best of my knowledge, if you take away our Dijkstra terms and then just zero out surface tension, I think we get back exactly what they got. They should be essentially equivalent.
The reason why I asked you is, as you pointed out, it's omega, it's directly related to nonlinear terms, right? So if omega becomes larger and larger, so nonlinearity becomes higher and higher. So maybe this approach is impossible for larger numbers of omega.
Yeah, you're gonna run out of road pretty quickly. I mean, if you go look at Phillips' work, so this is, mercy, what is his first name?
You talking about Bill Phillips, WRC Phillips?
Yeah.
Yeah, Bill Phillips.
Yeah, out of Australia. He has some work, especially so he has like a series of papers where he kind of looks at the perturbation theory that Craik did in the early 80s, and then just runs with it deeper and deeper and deeper and deeper. We almost certainly actually caught him as a reviewer, and he raised hell with us. Oh, mercy. Yeah, I mean, he made it all better. I mean, he really, really went to the mat with us. It was impressive, actually. I'm honestly grateful. Anyway, so he looks at essentially completely generic shear profiles, like you would look at if you were going to say do classic Rayleigh instability analysis. and then really does sit down and try and figure out how you're going to deal with a freely moving surface and all this stuff in a perturbation theoretic framework that really doesn't rely on any of the, plane wave style, modulation ansatz that I use. I think there are some technical difficulties that he maybe didn't sketch out quite as much as he ought to have, but that doesn't mean he doesn't have everything you basically need to do the thing. You know what I mean? I think you just have to carry it forward. Now, how manageable that's going to be, I'm not 100% sure. But yeah, I would generally say, like, in some sense, my results are lucky, that I got away with saying omega is order 1, right? And we have something interesting to say for. If it got bigger, that would definitely be problematic for my overall approach. Yeah, absolutely.
Okay, thank you very much.
You're welcome.
Any other questions? Okay, thank you very much. Thank you very much,
Yeah.
Chris.
Thank you so much for the invitation.
Nice. I really appreciate it.
Thanks again, Nick. And yeah, it was wonderful.
Thank you very much. Okay, thank you very much, all of you, again, for joining us today. Okay, today's seminar is now closed. Next seminar will be held on next month, on February 18th. I'm looking forward to seeing you again. Okay, thank you very much again for today.